So yeah, you can let me know when to get started.
You can get
Okay.
started. Yep. So
So-
we're very happy to have Ben Gammage for our first speaker this year.
It's an honor. I think the title I gave was Extended Langlands and Relative Langlands. Is that correct? If it wasn't, someone can correct me. So I'll just write that on the board. Extended Langlands and Relative Langlands. Everything I say is going to be based on joint work with Justin Hilburn. And I'll also mention at a certain point some work that we did that started off this project together with Aaron Mazelji. Yeah, and I haven't prepared, I don't know, exactly, I don't know if I prepared 2 hours worth of talks, so definitely feel free to stop me with questions. I absolutely encourage you to. There's sort of 2 talks that I can give here and sort of which, I don't know, I have 2 hours, so I guess I can do that. The first one is like just a whole lot of conjectures and sort of, I don't know, vague sort of, maybe some things are even not fully defined, and some of these conjectures are defined, but they're still very conjectural. And then there's some sort of concrete computations. So maybe in the second hour, I can, if people are interested, I can go into some of the actual computations we do. And in the first hour, I'll just kind of sketch out some of the broader program and conjectures and everything. Again, feel free to redirect me at any point or to ask questions. So, okay, so what's the geometric Langlands program? So if I have a reductive group, this is maybe not exactly the way physicists would say it. They would start with a compact Lie group. But if I have a reductive group, this is the sort of thing you might imagine you can use to define a gauge theory. So since this is the geometry and physics seminar, I should start out with some words of sort of the physics justifying what I'm doing. So this defines you a 4-dimensional super Yang-Mills theory. So 4D n equals 4 supersymmetric gauge theory. Again, which usually goes by the name of super Yang-Mills theory. So okay, this is some kind of object of not of mathematics but of physics, and part of what makes it an object of physics rather than mathematics is we don't really know what a quantum field theory is. This is a 4-dimensional quantum field theory, so it's kind of outside what we as mathematicians necessarily are able to study. But the reason why mathematicians like to study supersymmetric quantum field theories is they tend to admit topological twists. So what that means is that there's some portion of this theory that is a topological field theory, and topological field theories are something mathematicians do know how to study. So this theory has 2 topological twists, which are called you might call them the A twist and the B twist. So let me give these names. Let me call these A for G and B for G. So the G labels the gauge group, and the 4 labels that this is a twist of 4-dimensional supersymmetric gauge theory. So the cobordism hypothesis. Well, actually, before I say that, let me say one more bit of physics, which is whatever S-duality or the geometric Langlands conjectures. So the geometric Langlands conjectures are, in a nutshell, the program to establish that at least after this topological twisting, that this A-type twist of G gauge theory is equivalent to the B-type twist of some gauge theory associated to some dual group G check. So our goal is somehow to kind of to see if we can make sense of this statement. So the claim is that kind of everything in the sort of geometric Langlands program is kind of downstream of whatever this statement is, if we could make sense of it. And of course, implicitly, what I'm saying is that if you really understood what a quantum field theory was, then there's even a much better version of this statement, which is that like the full supersymmetric G gauge theory and G check gauge theory are equivalent. But that's maybe too complicated for us to discuss, so I'm restricting to an equivalence of 4-dimensional topological field theories is what these things are. Okay, so that's the kind of physics background to whatever it is that I'd like to talk about here. So the cobordism hypothesis, or whatever you'd like to call it, hypothesis, is essentially the statement that a four-dimensional topological field theory is equivalent to or determined by, in some sense, its collection of boundary conditions. And moreover, that the structure of those boundary conditions is for a four-dimensional topological field theory, it's a three-category. So for those of you who haven't seen this before, maybe I'll just draw the sort of the usual picture. So for instance, let me, since since it's hard to draw a four-dimensional things, let me draw one dimension down. So e.g., boundary conditions for a 3D TFT. So these, again, by the same logic, are supposed to form a two-category. So what is a two-category? It's something where I have some objects. Okay, here's the bulk of my three-dimensional TQFT. It's living inside of this cube, maybe. And then I can imagine that like a face of this cube is like a boundary condition. So here, maybe I have like a boundary condition. L1 is one boundary condition for my TQFT, and L2 is some other boundary condition. And then the point is that there's also some kind of interfaces where these boundary conditions can talk to each other. So I could think of that, like, whatever the structure of these boundary conditions is, there's some objects, which are these boundary conditions, and then there's some kind of HOMs, some kind of like one morphisms between them given by interfaces. But then those interfaces can have further kind of defects between them where I switch between interfaces. So this is maybe like I1, I2, I3. And so I should read this picture like this is a picture of something that's happening in a two-category, which is something where I have objects given by these LIs. I have some morphisms between them, and then I have maybe some two morphisms between those one morphisms. So this is a picture of why you might expect a three-dimensional topological field theory to give you a two-category of boundary conditions. Okay. So that's the kind of setup. Now let's start making some more mathematically precise statements. Before I do that, any questions about anything I've said so far? Maybe people can't really have questions because I haven't said anything so precise yet.
Could I ask a rather informal question?
Yes.
When you say twist, is there, without having any physics background, should I be thinking of something in particular when you say
what do you mean?
So I don't know what a topological twist of a quantum field theory is, but like, is there something you could say that I could keep in mind?
Well, yeah, maybe
Maybe the answer is no, and I just need to just
maybe like a toy example is something like if you think of the like differential forms on a manifold, like that forms some kind of like the space of all differential forms forms some like complicated infinite dimensional vector space. But if you turn on the de Rham differential, then like you get some chain complex that has some finite dimensional cohomology groups. So that's a sort of, in some sense, somewhat precise, thing of like what this topological twist is maybe it's like, something like turning on a de Rham differential. So you get something topological in the end instead of something infinite dimensional that depends on more structure.
Thank you.
There's sort of historical reasons why it's called a twist, but another way to think of it is like, yeah, if you restrict to some like inside the de Rham complex, if you restrict to like the things that are closed under the de Rham differential, then you can just take their cohomology and you get some finite dimensional thing that's only measuring the topology of your manifold. And again, that's a somewhat precise kind of thing. So okay, so there's some like inside of this complicated theory, there's some simpler piece, which is this topological sector. Okay. Any other questions? Okay, so I said that the geometric Langlands conjecture, whatever it is in its sort of fully extended formulation is an equivalence between two four-dimensional topological field theories. And according to this sort of formulation of topological field theories, this should be understood as a collection as an equivalence of three categories. So the question is, what are the three categories involved in this equivalence? So if we knew that, then I don't know, we'd know a lot more than we do right now. But in some cases, we can make this precise, namely in the case where my group G is a torus. So for the moment, let's restrict to the case where G is a torus. So it's Gm to the n, or in its complex points, or C star to the n. And so in this case, I'm just going to, from now on, use this notation A4G and B4G check to refer to this sort of relevant three category. So in this case, my A4G is going to be the three category of local systems of two categories over BG. So I'll explain what that is in a moment. Maybe I can think of the complex points of BG. So I get a sort of topological space. And my B4G, maybe B4G check, is going to be equal to the three category, again, of quasi-coherent sheaves of two categories on BG check. Okay, so I've at least written down some objects on the board that look sort of mathematical now. My underlying conjecture is that I have some equivalence of three categories, and now I'm telling you if my group G is a torus, then these are the relevant three categories. And you can try and ask at this point, what are these three categories? So there's okay, maybe I don't know. There's some maybe people are familiar with, like, if I erase these two categories, there's some notion that people might be familiar with local systems on a space, right? If I have a topological space, I can study the category of local systems on it, which is something like representations of the fundamental infinity groupoid of that topological space. And you can think about this as modules over chains on the base loop space of your original space by a kind of, or if you're simply connected, you can think of it as modules over cochains on your space. There's a causal duality relationship. Anyway, the point I want to make is that you can also think of this as the category of modules for something. This is going to be, you can think of this as a local system of two categories on here is a two category equipped with the structure of a module over local systems on the base loop space of this thing, which is just G itself. So an object of this three category is a two category BG check. And so what is local systems of categories on G? Well, G, so I mean, G is a torus, right? So if G is a one-dimensional torus, let's just for a second think about the case where G is a one-dimensional torus. A local system, I mean, a one-dimensional torus, C star is, its homotopy equivalent to S1, which is a K pi 1. So a local system of anything on a K pi 1 is just like whatever your fiber is together with, the fundamental group acting as automorphisms of it. So a local system of anything on a torus, on a one-dimensional torus, would be like that thing together with one automorphism coming from the monodromy around the circle. So a category with an automorphism. So in this case, of course, for a possibly higher dimensional torus, I might have more automorphisms. But so ultimately, what the data of a local system of categories here, it's the data of a category C. C is a category, together with a map from pi 1 of G into the automorphisms of C. This pi 1 of G also goes by the name of the co-character lattice of G. So this is not such a crazy object. It's a local system of categories is a category together with automorphisms for each loop in your torus. And so similarly over here, you can think about this quasi-coherent sheaves of categories on BG check, and quasi-coherent sheaves of categories on BG check. Actually, I can apply a one affineness result in this case. Just like I said before, quasi-coherent sheaves of two categories on this thing is like modules over quasi-coherent sheaves of categories. Quasi-coherent sheaves of categories on this thing is going to be modules in categories over quasi-coherent sheaves on BG check. Yes, categories. Yeah.
Why are you on the current pi 1 of GC instead of like the full?
Because it's a K pi 1, so it doesn't have anything besides pi 1. G is a torus.
Oh.
So everything on this board, G is a torus. So I only needed the pi 1 of the torus. That was the whole homotopy type of it. So over here, modules for quasi-coherent sheaves on BG check in categories. So quasi-coherent sheaves on BG check. So this thing is just rep of BG check. Now the monoidal category of representations of a torus is pretty representations of G check. And so the monoidal category of representations of a torus is pretty easy to understand. This thing is a semi-simple category. With simple objects labeled by the character lattice of G check, which is of course equal to the co-character lattice of G. And okay, I could go into more detail of what this category is, but hopefully at this point it's starting to become clear, how you would establish an equivalence between these two sides here. That like, a category, this two category, an object in this two category is a category together with a module structure over this thing, which means that for every one of these objects, you're supposed to get some functor from that category to itself. And each one of these objects is an invertible object in here. So that functor is going to be an automorphism and they all commute, et cetera. And you put it all together and you find out that there is in fact an equivalence between local systems of categories on G and quasi-coherent sheaves of categories on BG check. And if I were more careful about everything I was saying, then you would have noticed that this was actually a monoidal equivalence. So this does in fact establish the equivalence that I claimed at the start between local systems of two categories on BG check and quasi-coherent sheaves of two categories. Sorry, local systems of two categories on BG and quasi-coherent sheaves of two categories on BG check. I used well here I mean I used what this two category is uses it. And over here, like the rep G check is more complicated if G check is not a torus. I mean, it's still a semi-simple category and it has the same symbols, but now the 6J symbols are different. I mean, you know, if I take two, like the tensor product of two symbols might be a direct sum of more symbols. Yeah. So yeah, I mean, you're going to have to repair this this equivalence somehow. You're going to have to move to like incoherent sheaves and things like that of categories. No, that my formulation of what these two categories are. Yes. So for a general G, we're going to have to modify our understanding of what are the relevant two categories here. Okay. So luckily, in the case of a torus, like the situation was relatively simple. So I haven't yet suggested what the full the three categories should be for a general G. Maybe I can start to ask that now. So okay, this board was all about a torus, and so what about general G? Not necessarily a torus, and well, okay. So let me say first of all that the full three categories are not completely known. On the B side, we're close to maybe knowing a lot about what the three category is. On the A side, we're really not. But like, let me kind of back up and give a different perspective on how you might think about these three categories. Which is one way you might try and think about them is you might say like, well, do I know, you know, I could use this, you know, one thing you could do if someone gives you some purported equivalence of three categories and you don't know what the three categories are, is you can say, do I know what some of the objects are and how they match up? And then I could maybe take HOMs of them and get some two categories. And then I could see if those two categories are equivalent, for instance. So I know that some objects in these three categories, maybe let me give a little heuristic that objects should be given by Hamiltonian G spaces so some kind of space M, some kind of symplectic space M together with a Hamiltonian G action. And then I can ask if I have, you know, two of these spaces, they're HOMs. HOM of you know, so I have one Hamiltonian G space G acting on M. I have another one, say G acting on N. And the HOM between these, there should be some two category. Associated to, so one thing I can do if I have two different Hamiltonian G spaces is I can produce a new Hamiltonian G space by taking the product of M and then taking the Hamiltonian reduction by the diagonal G action. And so this will produce me some sort of space that still has a residual Hamiltonian G action, but is obtained by sort of combining these two in some way. So in either case, either the A side or the B side, the HOM between these two objects should be some two category which is associated to this thing. So call this two category. I'll call it like A or B. I'll call it A3G of whatever this thing is, or B3G. Maybe I'll fill this in of this space. M times N. G times yes. maybe I don't need the G anymore. I don't know. I'm not sure where I'm going with this notation. But anyway, there's some kind of 2 category which you can associate, which is going to be a HOM inside this 3 category between these 2 objects. So I'd like to kind of connect these stories again. Maybe so. Let me do some example of where G is a torus. Yes. So derived stacks. I don't know. I mean, there's some kind of spaces with a Hamiltonian G action, and maybe in nice cases they are actually manifolds. Oftentimes they are, but I think derived is important because they're usually sort of in some shifted cohomological grading. Yeah, I would say you can think of them maybe as like derived algebraic varieties or whatever sort of category you like that includes sort of cohomological shifts and also like things that have a notion of symplectic structure. Well, I'm going to say what happens when M is a point. Yeah, so maybe. So let me do the example of where G is a torus again. So I'm moving to this board now. The 2 simplest examples. So the 2 simplest examples of Hamiltonian G spaces, where G is a torus, are I could take M to be G itself, or I could take maybe I should. Maybe let me write it this way. I can take G acting on G itself, sorry, T star G. So, right, the simplest way to get a Hamiltonian G space is just let G act on any space and take its cotangent bundle. So anything that has a G action becomes a Hamiltonian G space by passing the cotangent bundle. So the 2 simplest examples are G acts on itself and then gets a Hamiltonian G action on its cotangent bundle, or G acts on a point and then gets a Hamiltonian G action on the cotangent bundle to a point, which is, of course, just a point itself. And in fact, not only are these the 2 simplest examples, but in this case, these are exchanged by the duality. These objects are exchanged by the geometric Langlands conjecture. So maybe I'll put a G check over here so it makes clear what I mean. That on the one hand side, I have G acting on T star G, and on the other hand, I have G check acting on a point. And my claim is that one of those gives me an object in one side of these 3 categories, the other one gives me an object in the other 3 category, and those objects are supposed to correspond to each other under this equivalence. So you can try and now like perform that check. So let's see what sort of the HOMs between these things should be. So if I take T star G and T star G, well, that's the same thing as T star of G times G. And then if I take a Hamiltonian reduction by the diagonal G action, that's the same thing as T star of G times G mod G, which is just another copy of T star G ultimately. So okay, if I go through all this stuff of taking T star G times T star G and take a Hamiltonian reduction, then I just get back T star G in the end. Similarly, if I take T star of point times T star of point, which is just T star of point, and take a Hamiltonian reduction by G, that's T star of point mod G, also known as T star of BG. Oops, except these should have been checks over here. So now I can take my sort of A twist here. I said that whatever this whatever the HOMs between these objects should be some 2 category. And in the A twist, that 2 category associated to this thing, I claim is going to be the 2 category of local systems of categories on the base of this cotangent bundle. Local systems of categories on G. And over here, if I take the B twist, then I'm going to get quasi-coherent sheaves of categories on BG check. So this sort of did match up from what I was saying before, that kind of each of these 3 categories before had a single generator. And now I'm telling you in these terms what that generator was. That generator was the Hamiltonian G space of respectively either T star G or a point. And this was the equivalence I sketched before. And of course, you could do this the other way as well. You could ask for what's the B twist of this and what's the A twist of this guy. So the B twist here, you'd get quasi-coherent sheaves of categories on the base of the cotangent bundle, quasi-coherent sheaves of categories on G. And over here, you could get local systems of categories on BG check. And once again, I claim that, by the same logic as before, you could match these things up here. Okay, so that's some prediction of what's some of the structure of this equivalence. And now, okay, I do want to talk about non-abelian groups at some point, but maybe first of all, I'd like to say a little more about this torus case. So in this torus case, you could also consider there are other interesting objects. So other interesting objects for G a torus. So you can ask, what are the other interesting Hamiltonian G spaces for G a torus? And the answer is basically toric varieties, or rather cotangent bundles of toric varieties. Right, a toric variety is our sort of favorite example of a space that a torus acts on. It's a compactification of the torus itself, where the torus action extends to the compactification. So these sort of generalize this example of G acting on T star G. Like if G is C star, then C star acting on T star C star extends to an action of C star on T star C. So I'd like to consider this because now when we start considering these examples, we're going to find that we have to generalize these categories, these two categories that we were considering before a little bit. So let me give an example of the duality here. So example, once again, if G is a one-dimensional torus, say G is GM, then in this case, oh yeah, I maybe didn't make this clear, but my notation is consistent that I'm using G check, both for the Langlands dual of a reductive group and for just the dual torus of a torus, and those things agree for tori. So the dual of a one-dimensional torus is also a one-dimensional torus, and under this duality, I have my favorite object, like I said, that's besides these, is G acting on T star A1. And that gets exchanged under the duality with G check also acting on T star A1. So these T star A1 and T star A1 form a dual pair. And so the prediction, one prediction you could make is you could pair like this object with that object I talked about above, and similarly pair this object with that object you get above, and the HOMs should be the same. So prediction, which is that HOM in this A4G3 category between this object, G acting on T star G, and G acting on T star A1 should be equivalent to HOM in this B4G check category of G check acting on a point paired with G check acting on T star A1. And what you're going to get when you do this thing is you find that like pairing with this guy has the effect of just passing to the underlying space here. Right, for precisely the reason that kind of if I multiply by T star G and then take a Hamiltonian reduction by G, that just undoes the T star G factor. On the other hand, this one, pairing with this guy, has the effect of just do a Hamiltonian reduction on this guy. Because pairing with this, multiplying with this does nothing, and then you take a Hamiltonian reduction. So this is going to predict an equivalence between whatever my A3 category is, this A3G of T star A1, and my B3G check of T star of A1 mod GM. And this is supposed to be some equivalence of two categories.
Ben, can I ask a question?
Yes.
How can I think of a Hamiltonian G space as giving me an object in these three categories?
I don't know. You sit and think real hard until I mean, I don't know. I've sort of defined it this way. I mean, I like somehow these three categories had no independent definition otherwise. Like I said that like we don't know what these three categories are, but I'm stipulating that like a Hamiltonian G space gives you some object in them.
Oh, I guess like on the board above there, you wrote that A4G is local systems of two categories.
Well, that was okay. So
BGC.
in the torus case, I did tell you something.
Right. So I
and
guess I'm wondering if I have a toric G space or like
right.
that.
So I mean, right. So what you should imagine is let me roughly speaking, okay, imagine that I mean, imagine you had a Hamiltonian G space where the G action was free. So like not on T star A1, but T star G satisfies this, for instance. In that case, like the Hamiltonian reduction of T star G like has a map to T star BG. Like that's sort of what you can think of a Hamiltonian G space as being something that has a map to maybe one shifted T star BG. Or is it just T star BG? I think, yeah, a Hamiltonian G space is something that has a map to one shifted T star BG. And like each of these categories you can think of as like, if something has a map to you, if you're looking at like whatever, like local systems of categories on X and something has a map to X, then you get a local system of categories by taking the like fibers of whatever's going on above. Or similarly, if something has a map to BG check, then you get a quasi-coherent sheaf of categories by, again, like taking the fibers kind of and putting them all together into a quasi-coherent sheaf of categories.
Okay, that makes sense. Thanks.
Like, this is a little bit like, you know, if someone asks you, like, what are, you know, sheaves on a space, like just in general, if someone gives you a space X and says, what are sheaves on X? You could give some definition of what are sheaves on X, but you might say, I'm really most interested in the sheaves of geometric origin. And a sheaf of geometric origin is like, I take some space Y that maps to X, and maybe I put some restrictions on what that space Y can be, like it should be proper over X or something. And I say, I'm only interested in like the push forward of the constant sheaf of Y. And like that gives you a hugely rich collection of sheaves as you sort of range over all objects Y. And that's what I'm doing here.
Cool. Thank you.
Yeah. So
but actually, if you push this analogy further, then it's not clear that the only objects you get are just Hamiltonian G spaces, and maybe you can get some more general objects, which you can, because if you can see the sheaves of geometric origin, if you sort of generate, I don't know, triangulated category by them, then you get more objects there. So I don't.
Yeah, perhaps so. No, thank you. That's an excellent point. I'm certainly not maybe going to claim that these are all the objects, but these are some objects that we have some control over, at least.
Here, the geometric objects generate. Like in this example.
Oh, well, certainly in this example, I had my three categories was each generated by one object.
Yeah.
Yes.
And that was geometric.
Yes, and I think this is still going to be true in general, but there's also, you know, some questions you can ask about sort of higher categorical homological algebra and like what it means to generate. And, maybe, yeah, maybe that's not relevant. But yes, certainly in this talk, I'm only going to restrict to kind of like things of geometric origin, so to speak. And that's why I'm like thinking of whatever my objects are, they're these Hamiltonian G spaces. So maybe this is a good place to say that like now is the time in my talk when I'm going to expand beyond these two categories I was talking about before. So I said that kind of maybe just to repeat what I said out loud a second ago, if I have a space X and I have a fibration over X, then like I get a local system of whatever over X just by taking the like something associated to the fibers. Some category or some two category or some vector space or whatever associated to the fibers. If my map were a fibration, then that thing should vary locally constantly, maybe, and I get a local system of categories. But like if it were not a fibration, like for instance, if my G action had fixed points on this thing, so the map to BG is no longer a fibration, then I should get something more interesting than just a sort of local system of categories somewhere. Or likewise over here, it turns out even on the B side, like if I have a map that's not smooth to some space, then I should get more than just a quasi-coherent sheaf of categories on the base. I should get some like incoherent sheaf of categories. So now I'm going to sort of justify that. So so I've sketched this proposed equivalence of two categories here, but now I need to tell you what these two categories are. So maybe I'll move back to the first board. And I can ask, what are these two categories? So these two categories are richer than the ones we studied above. So as I said previously, my two category I studied, I had these two categories like A3G or whatever, and those two categories turned out to be something like local systems of categories or something. The reason for that, the reason why I want some richer two categories is that, like, for instance, if I on the A side, I could say, like, okay, here, when I, whatever I'm doing, I want it associated to T star A1. But if I were to just study local systems of categories on the base of that cotangent bundle, like I did before, well, okay, first of all, this two category would be kind of stupid. It's not that interesting, right? I mean, A1 doesn't have many interesting local systems on it, and it doesn't take into account the orbit structure of G acting on A1, right? Which seems like at least sort of relevant that, like, this whole thing was kind of like in the framework of, we were studying A1 in the context, or T star A1 in the context of like being a toric variety with G acting on it. And so the sort of joint resolution to these problems is that, well, let me maybe justify this in another way. Let me try and think about what this two category A3G of A1 should be, whatever T star A1. And let me sort of think about it in exactly the same way I did before. So whatever this two category is, objects of it should come from some space X mapping to A1. And maybe what I'd like to require is that this is a fibration over the GM part. Over the GM inside of A1. Again, this is to sort of like take into account the fact that, like, this is one G orbit. So I don't want anything interesting to be happening within that G orbit, but something interesting can happen as I change G orbits. So if I sort of did this, then what kind of object should this give me inside of here? As I said, you could take some category associated to each fiber and get a local system of categories on the GM. But then you'd also get some extra data at 0. So the thing you get is no longer a local system of categories on A1, it's a local system of categories on GM, but then you can also have something interesting happen at 0. And this is supposed to justify that a good name for whatever this two category is of T star A1, a good name for this two category might be the two category of perverse sheaves of categories on A1 that are constructible with respect to the GM action. So I have not at all defined this two category for you, but I've told you that, like, there ought to be some kind of two category whose objects should be things that are like one category level up, but they mimic what happens when you study something like perverse sheaves on a space. That, like, this is some whatever perverse sheaves on a stratified space is, or even constructible sheaves on a stratified space is, it's something that is like locally constant on the various strata, but then interesting things can happen as you kind of glue between strata.
But why perverse?
Right.
Why do you necessarily want want something like perverse?
Yeah, that's a good question. I mean, so I could have various answers to it. One is that I don't know. I mean, this is just a name, like, you know, like, right. I mean, you know, one thing that you could, I mean, one thing that you could ask is like, there's, you know, there's something that, okay, I mean, in some sense, this is just some, you know, some name that like is formulated in this way to make things work out. I mean, Kapranov and Shechtman gave some definition of what a perverse sheaf of categories is in one particular example, namely this one. And it works out in this case. But something you could ask is like, well, why didn't I just say constructible sheaves of categories? Because that's something that maybe has a more well-defined you know, notion. That's something that makes sense for any space. You can ask for like a representation of the exit path category of the space inside of categories. And I don't know, somehow like I don't have a good answer to why, but like this turns out to be the thing that works out in this case. It's possible that they're like ultimately, like maybe you, like the way people often define perverse sheaves is like a perverse sheaf is defined as like perverse sheaves are defined as the heart of some T structure on the derived category of constructible sheaves. And maybe if you had a good enough categorified homological algebra, you could define like the derived two category of constructible sheaves of categories, and then find some kind of like T structure inside it that gives you that thing. My understanding is something like that might be.
Well, but that's precisely the question.
What?
I mean, that was precisely my question. Why are you after T structure?
Yeah, so I don't know, but you know, in good like in the one categorical setting at least, you don't lose anything by passing from constructible sheaves on A1 to perverse sheaves on A1 with this stratification. Those two, you know, derived categories are equivalent. So it could well be that you don't lose anything in this case. My actual answer is just perverse sheaves are much easier to categorify because they have fully linear algebraic descriptions. So we have a better chance of knowing what these two categories are right now. That's the best answer. I mean, maybe eventually there will be some version of this that involves constructible sheaves also, but the perverse sheaf story is easier for us to access at the moment.
Maybe one comment is one level down, you expect that holomorphic Lagrangians give you perverse sheaves,
Mhm.
the micro-local sheaf correspondence. And this is supposed to be an analog, and well, also you might want something more general, but it's not clear what the correct notion of local systems of categories.
Yes. I will say that ultimately, like these A3G, et cetera, have some like fully analytic definitions. Maybe the A4G is outside of reach right now, but the A3G does have some like totally, you know, should have some analytic presentation in terms of like objects are holomorphic Lagrangians, maybe with some extra data on them, like with a local system of categories or something. And then HOMs are calculated by, you know, taking intersections of those Lagrangians, and then you calculate two morphisms are calculated by some holomorphic strips, and then the composition is calculated by these Futter balls, these three-dimensional balls satisfying the Futter equation, and that is sort of very tuned to the perverse T structure somehow. So yeah, this is just repeating what Nick just said. But you know, I do think that once I'm about to say and haven't stated yet, it is true that kind of so I'm about to state an equivalence, like perverse sheaves of categories on something looks like incoherent sheaves of categories on something else. And I find that like those kind of T structures don't match up in the sense that like, you know, especially when you decategorify and you get some statement like sheaves on something is coherent sheaves on something else, you find that the perverse T structure on one side really corresponds to like a causal T structure on the other side. So there's maybe more than one interesting T structure to consider, but from the A side, the natural T structure for me really is this one for various reasons. Okay, so maybe I should state a a theorem, and then we can have a break. We're supposed to have a break at 3, I'm told. Is that okay? So so let me say that. Okay, so I've told you some name of this thing. I didn't tell you what this 2 category is, but I told you a name of the 2 category. And similarly, this B3G check of T star of A1 mod GM. This thing should have some name, and the name of this thing is incoherent sheaves of categories on A1 mod GM. So whatever this 2 category is, it's similar to quasi-coherent sheaves of categories, but it has some more generators. Basically, the thing is that quasi-coherent sheaves, maybe one way to say it is that like quasi-coherent sheaves of categories, if I thought of the objects as given by mapping, mapping to whatever my base was. Like if I think of objects, stacks with a map to this thing, then like previously I only allowed smooth maps, but now I allow maps that are no longer smooth. Maybe I'll just write that here. Objects include. Maybe I'll write it this way. This 2 category has 2 generators. On this side, yes, except I think it's full singular support because this thing is just a point. Yeah. So this 2 category has 2 generators, namely A1 mod GM mapping to A1 mod GM. So this is the generator whose endomorphisms gives me quasi-coherent sheaves on A1 mod GM. That's like the one of the Hom spaces that I found before. But then I also have another one, 0 mod GM, mapping to A1 mod GM. And so this is a new generator that I didn't have in my quasi-coherent sheaf category. So this is whatever this 2 categories, it's slightly bigger than quasi-coherent sheaves of categories, precisely to account for the fact that I might want things that that behave differently as I cross the strata of the GM action here. So now let me just state a theorem. This is me, Aaron Mazelji, and Justin Hilburn. And it is precisely the statement that you now expect. Perverse sheaves of categories, GM constructible perverse sheaves of categories on A1 is equivalent to incoherent sheaves of categories on the dual A1 mod GM. So I have not defined either of these 2 categories, but this is an equivalence of 2 categories. So whatever these 2 categories are, this should count as some evidence that my program makes sense. So after the break, I will talk about some decategorifications of this statement and how you can take trace to obtain some statement about loop spaces. And then I'll also talk about conjectures for general groups G. And then I'll maybe go into more details if people are interested about what these 2 categories actually are.
Can you switch sides on this theorem?
The what? Oh, yes. Yeah, sorry. You're right. The theorem is stronger than I stated. It's an equivalence of 2 categories equipped with an action of, so this category has an action of local systems of categories on G equals GM. And this category has an action of quasi-coherent sheaves of categories on BGM. This is a monoidal category. These monoidal categories are equivalent, I said before, and basically, I know the full, since I know the full sort of statement of geometric Langlands, in this case, I can kind of gauge and ungauge these 2 categories. So yes, I can also produce an equivalence that's like perverse sheaves of categories on, maybe like, yeah, GM, whatever, GM or S1 equivariant perverse sheaves of categories on A1 looks like incoherent sheaves of categories on A1 with a certain singular support condition given by conormals to the GM strata. So
okay, in particular, left-hand side of this is well-defined.
The left-hand side of this is well-defined. So the point is that this 2 category here is a 2 category with S1 action. Like there's some automorphism of the identity functor coming from the S1 action, and you can trivialize that automorphism of the identity functor. It makes sense to ask for a trivialization of that. And asking for a trivialization of that, it turns out that automorphism of the identity functor corresponds to like tensoring with O of 1, like the structure sheaf twisted with the weight 1 over here. So trivializing that corresponds to like D equivariantizing over here. Any other questions about this statement? I mean, besides what's the definition of these 2 categories? Okay. Do we have a break? Okay. When do I start up again? So where was I? I claimed, okay, people might come back or they might not. Hang on, I'm trying to shove this battery pack back up. Oh, probably still good. Someone will let me know if I did something wrong here. Okay, so where we ended was that I stated a theorem without defining either side of the theorem. It's the best way to do it. Then no one can check whether your theorem's right or not. Actually, the best way is probably just to define only one side. And then like, and then if someone asks you how the proof is, you go, well, you know what the other side is. It's the same as the first one. Okay, so I might at some point in my talk like to go back and actually explain what these two categories are. But first, I'd like to boldly press on and say what some consequences are that might be more appealing to people that don't involve two categories. So if you don't like two categories, and why wouldn't you? I don't know, two categories are great. But if you don't like two categories, we can take categorical trace, also known as factorization homology on a circle, to get an equivalence of one categories. So this is another theorem of myself and Justin Hilburn, which is that maybe before I state the theorem, let me get some notation. So I'm going to write fancy L of C is going to be defined to be the geometric loop space of C. So this is the in scheme that is often called C of K or C formal Laurent series T. This is the loop space. This is the geometric, I'll call it loop space of C. And on the other hand, I'll write sort of normal L of A1 mod GM for the Betty loop space of A1 mod GM that's maps from S1 into A1 mod GM. I guess this is related to what people often call the inertia stack. But this is this is what I would call the Betty loop space. And so our theorem is that the category of constructible sheaves on this loop space of C, which are constructible with respect to the stratification given by the action of the arc space of C star, is equivalent to the category of incoherent sheaves on the loop space of A1 mod GM.
Arc space.
Yeah, the arc space. The arc space is C formal. I mean, arc space of C star is C star of whatever. Well, I mean, it's the it's the arc group of C star. Yeah. So all I'm saying here is that this is the stratification. So the loop space of C. So what is the loop space of C? It's formal Laurent series, and it has a natural stratification given by like what's the lowest order term in your Laurent series, and that's just this stratification here. So each stratum is a copy of C star times an infinite number of copies of C, and it's that stratification. And so now I can make the precise the statement I said before, that kind of like this this notion of perverse sheaves of categories comes with a sort of natural kind of T structure on this thing, and likewise coherent sheaves of categories also gives me a natural T structure on this thing, and the perverse T structure on this side does not match up with the coherent T structure on this side. The constructible T structure here does match up with the coherent T structure. But on the other hand, the sort of perverse T structure matches up with one that's, maybe a little more microlocal or something over here.
Sure.
I can make that precise, but
The question doesn't matter that it's C in this theorem. It's just some field of characteristic 0.
well, so I like to take C on my A side. So I know that I wasn't always doing this, but I really do like to take C on my A side, because on the A side, it's really something about like polymorphic symplectic geometry. So, and the idea here is that like over here, I can take any coefficients, and those coefficients, I mean, I can take this to be defined over any whatever ring or something, but that ring is going to be the ring of coefficients for my constructible or perverse sheaves over here. So it's the usual kind of thing that happens in Langlands, where sort of the coefficients on one side are the ring of definition on the other side.
There, as written, the left-hand side does not make sense for anything other than the numbers.
Yeah, because I'm talking about like actual like sheaves on a topological space. That's why when I was up here, I guess I was sort of careful. I was writing C there because when I was writing about local systems like on C star, like, you know, it didn't really, I mean, I don't know, maybe you can make this make sense in other contexts, but always I want to think of the A side as like an actual complex space of some sort.
You know, what they mean is that S1 here is treated as just like an algebraic stack.
Oh, this S1, this is the Betty, yeah, this is the Betty stack associated to S1.
So you can make sense for any field.
Over here, yes, this can be defined over any field. This over here is really something over C.
Yeah, the sheets.
But you can make some like a dull sheets.
Then the statement would not be true. You have to modify.
Yeah, I mean, there are probably ways, maybe Nick knows ways of fixing this statement for other kinds of sheaf theories. But for me, I'm very interested in having C be on the left-hand side here. Okay. So yeah, so this, oh yeah, and sorry, the statement is actually stronger than this, of course. The statement comes with the actions, the traces of the actions that I mentioned before. So if you take trace of this local systems of categories on GM, which is equivalent to quasi-coherent sheaves of categories on BGM, then you find that actually this is an equivalence, you know, that matches up with the actions on either side of on this side you have local systems on the loop space of C star, and on this side you have quasi-coherent sheaves on the Betty loop space of BGM. Which, you know, this equivalence is, you know, the Betty version of class field theory. I mean, it's pretty simple in this case. The loop space of C star is homotopic to the free loop space of C star is homotopic to like S1 times Z, because this is homotopic to S1, and then you just have a winding number of your loop, which is Z. And over here, the loop space of BGM is BGM times GM. So the coherent sheaves on BGM corresponds to local systems on Z, and quasi-coherent sheaves on GM corresponds to local systems on C star. Sorry, I said that fast, but these things act on either side. And so, you know, in particular, using this equivalence, you could since you know how this thing acts on here, you could you know, switch the role of GM on either side. So you could get a version of this statement that's also about like sheaves on the loop space of C mod C star over here, maybe, and on the Betty loop space of A1 over here. Although there's some, I mean, ultimately the statements that I want to make are most, we know the most about these kind of loop spaces when your thing you're taking loops on is affine. If it's not, then I don't know, but okay. So before I would like to say some more about this, but actually before I get there, I'd like to lay out what are the conjectures for how this picture kind of generalizes for a more general group G. Yeah, so so for a more general group G, for more general groups G, So now I'm back to this question of like, what exactly are my three categories for a general group G? And I said, I don't know, but our sort of first starting point is that we know what some objects are, and we know a couple of objects that get exchanged. So suppose we know a couple of objects like G acting on T star X, and maybe that's exchanged with G check acting on T star X check. These maybe don't both have to be cotangent bundles, and in fact, it's rather rare that they are, but just for simplicity of notation in this talk, let's keep this. Then we could pair them with other objects we know to obtain conjectures. Then we could pair them with other dual pairs to obtain some conjectural equivalences of two categories, just like we just did. So what we said here is that I had two objects I like, T star A1 and T star A1, which I happen to know were exchanged under this duality. And then I paired them with these guys, and that allowed me to produce some conjectural equivalence of two categories. So I want to do the same thing, only now, of course, this thing about for a torus, my two favorite objects of G, T star G and T star point being exchanged is no longer quite true. T star point is now going to go to Whittaker. So instead, maybe let me say a different pair of objects I really like, which is that I like T star of G mod N. N is the unipotent radical of my favorite Borel. So G acts on this thing. It's a Hamiltonian G space. And this should get exchanged with G check acting on T star of G mod B. Sorry, G check mod B check. So if I pair some things together, if I pair together my X and X check with this, then I obtain a conjecture. And that conjecture is that if X and X check are as above, if X and X check are as above, that is, if they are part of this conjectural duality like this, that G acts on T star X is dual to G check acting on T star X check, then my expectation is that perverse sheaves of categories, B constructible perverse sheaves of categories on X should be equivalent to int coherent sheaves of categories on X check mod B check. Let me also require that this X and X check are spherical varieties. So spherical varieties means that that the open orbit of B check on X check is just going to be a point, and same with the open orbit of B on X. I mean, sorry, it's going to be dense. So that's
about your notation. Sorry, X check is T star G check mod B check, or G check mod B check itself.
It's this I wrote up here. So sorry, X check is neither of those things. What I did was I took X check and then I paired T star X check with T star G check mod B check. So that's what gave me the right-hand side here. So this is an equivalence of two categories. And so this two category I got by pairing two objects in my conjectural geometric Langlands 3 category, namely this object here, G check acting on T star X check, and this the G check acting on T star G mod B, G check mod B check. And similarly, I took this object and I paired it with this object here to produce the conjectural left-hand side two category here.
Sorry, when you're saying that X is dual to X check, is it just some like phenomenological combinatorial duality between some data that defines spherical varieties? Or...
Right. Yeah, this is sort of a philosophical question. What does it mean if I don't know what the three categories are? What does it mean to know that these two things are dual? I mean, there's various answers you could give. I mean, one answer is that like if I start with G acting on T star X, then, you know, maybe I could kind of turn the crank and run this Coulomb branch construction, and that's going to pop me out some other space here. And in this case, maybe it's this space. That does seem to be, I mean, you know, and obviously there's, you know, enhancements of the Coulomb branch construction, and that does seem to be our state of the art. Sasha can correct me as far as knowing like what, you know, as far as predicting what dual pairs are here. I mean, I don't necessarily have
The only thing
better...
you shouldn't call this Coulomb branches. It has absolutely nothing to do with Coulomb branches.
Well,
No,
okay.
no.
I just mean,
It's about sort of constructing best dual right. It's
okay.
really absolutely nothing to do with Coulomb branches.
Okay. Yeah. So there's constructions. I mean, there's physical constructions by. I mean, this whole thing of like S-dual boundary conditions goes back to I think Gaiotto and Witten back in maybe 2009, and they gave, you know, sort of string theory setups for how you should expect to obtain dual pairs here. And, you know, there's some set of combinatorial rules you can use, like if you have a quiver variety for figuring out what the dual thing is, and so forth.
You can say it abstractly mathematically, and you know this, but it's just not. It's a construction which is somewhat similar to Coulomb branch construction, but it's a different construction. It's not the Coulomb branch constructions.
Right. Yeah, because this is the relative. This is for relative pairs and not just for the 3D mirrors itself. So yeah, there are ways that you can construct this. Maybe I won't say them in this talk, but you know, we have various.
I'm just objecting calling this Coulomb branch construction.
Okay. Okay, I withdraw, but I just I'm being recorded, so hopefully, yeah. But there's various ways that you can produce conjectural dual pairs here. And I'm saying that once you have a conjectural dual pair, and you know, there's various lists of them that you can find, you know, in various places online, and in various papers. And once you have one of these dual pairs, then I'm telling you that here's a conjecture about them, that like sort of. I mean, unfortunately, this conjecture is not really well formed because, okay, the right-hand side we do have a definition for. It's not really in the literature, but thanks to Arinkin and various other people, Stefanich, whatever, we have a, sorry, this should have been incoherent sheaves of categories on here. Everything was a 2-category. We do have a somewhat good notion of what this like incoherent sheaves of categories thing is. This thing we don't yet have a good definition for in general. So in a lot of cases, outside the sort of toric case. And as I'll say a little bit later, there's maybe some cases that you can reduce to the toric case. And so this sort of conjecture is in some ways sort of a, you can read it the reverse way of like being, you know, not a conjecture about X, but a conjecture about like what this 2-category should be once we learn how to define it. So this is sort of giving us some hints about what this 2-category should look like. And you know, because we already know, for as Sasha said, there is a construction that you know allows you to predict in a lot of cases mathematically what these dual pairs are. And so once you have that, that allows you to get a lot of data about what the 2-category perverse Schober's on various things with various stratifications should look like. Yes. So yeah. So the best, I should say that the best situation here is to run this duality for X equals G mod N itself, and X check equals G check mod B check. So X equals G mod N. And in that case, what you're going to get is you're going to get a conjectural equivalence between perverse sheaves of categories B times B stratified perverse sheaves of categories on G, and incoherent sheaves of categories on G check mod B check mod B check. And this should be a monoidal, this should be an equivalence of monoidal 2 categories. And these 2 categories ought
Why
to
is
be
it B
called...
times B constructible?
What?
Why is B times B constructible and not N times N
well, I mean, it's N times N. It's okay. It's N times N equivariant sheaves on G. N equivariance and N constructibility is the same thing, since N is a unipotent group. And then the sort of B constructible is just saying that I still want to. It's the same thing as what I did over here. I said that I really wanted like C star constructible perverse sheaves of categories on C. Like I wanted like all the possible monodromies there, but I wanted them to be a local system on that C star orbit. So it's the same thing that's happening here. So it's I mean, this is the
So
way
this is kind of arbitrary. That's
the what?
I mean, this is sort of arbitrary decision at this point. It's not part of your general logic.
Maybe so, but yeah, I mean, yeah, but it follows the pattern you use when you're defining the sort of universal monodromic Hecke 1 category, right? That you know, there's this paper of Jeremy Taylor on like what's the Hecke category, the universal monodromic version of the Hecke category, and it's some category of B times B constructible sheaves on G, which you can also think of as B constructible sheaves on G mod n, or T constructible sheaves on G mod n mod n. But like it does seem to be important to impose that torus constructibility there so that you have like finitely many strata. So yeah, these are.
I just don't see how this speaks with this framework that you declare that some things are dual to each other and then you pair them. Somehow within this process of pairing, somehow something becomes constructible for some reason.
Yeah, I mean, I understand that I've not given a fully satisfying answer, although I mean, I can say that you also should have objected before, because already I did this trick in my like when I was doing this thing for A1 already. But like for A1,
Yeah, I should have. Yes, I should have.
And yes, I don't have a satisfying answer there, except that like I have no idea what the category of all perverse sheaves of categories on A1 is, like with no stratification. That seems enormous, and like I don't know. I have no way of dealing with that, and but you know, if I impose this GM stratification, then I do have a way of dealing with it. I mean, the other thing to say is that in symplectic geometry, like when you study like a real symplectic manifold and you're studying its Fukaya category, you're often interested in reducing everything to calculations along some Lagrangian skeleton. And you want that Lagrangian to be like, you know, I mean, you want it to be Lagrangian, like the conormals to some stratification or something. And so like if I just studied A1 with no, you know, like if I just studied like all coisotropic things on there, that would be too big. But like imposing this GM thing imposes a Lagrangian singular support condition. So I don't know. This has something to do with like nilpotent singular support. So if you believe in nilpotent singular support, then you know, maybe you can believe in this too. That's unfortunately all the justification.
So you think that somewhere when you formulate this kind of equivalence of three categories, then somewhere there will be words about nilpotent singular support, and these words will, in this example, dictate that you will have to consider things to be B times B constructible.
Possibly so. Yeah, I do kind of believe that somewhere in the three category, it must have known that like when I pair these objects, that I still really want to keep in mind that yeah, that I'm constructible with respect to the orbit stratification there. Again, I don't have you know, another great way of justifying that. But so this is the conjecture anyway, that like there should be some equivalence of these Hecke 2 categories. And again, like it's possible to make sense of this right-hand side. And so sort of this is, I guess this talk at this point is a report on sort of like work in progress of me and Justin of like trying to figure out exactly how to define this left-hand side to make these things match up. And you know, this statement here, I mean, this statement should really deserves the name of like tamely ramified like extended Betty Langlands or something, tamely ramified Langlands conjecture. In the sense of like, I said that there were some three categories and I didn't know what they were. And okay, now I've written down an equivalence of three categories because a monoidal 2 category is the same thing as a 3 category with one object. And these three categories are like the part of the Langlands 3 category that like can be seen by this boundary condition, the T star G mod n or T star G check mod B check boundary condition. So that's the sort of tamely ramified part. So again, I don't know, I feel like we're somewhat close to formulating this 2 category, but it's hard to say. So that's the best statement. But then afterward, you can take trace of this whole thing. So now let me move over here and take trace. Just like previously, I took trace to get an equivalence of 1 categories. So given an equivalence of 2 categories, you can take trace, and what you do is you trade off a categorical level for a loop level. And then the conjecture at this point becomes that sort of sheaves on the geometric loop space of X that are I constructible with respect to the Iwahori subgroup of the loop group of G, that this should be equivalent to coherent sheaves, maybe incoherent sheaves, whatever, on the loop space, on the Betty loop space of X check mod B check. And that moreover, these things should be equivariant for the actions of the traces of these things, which should be like sheaves on Iwahori times Iwahori constructible things on the loop space of G versus incoherent sheaves on the loop space of B check on G check mod B check mod B check. And this equivalence down below is the equivalence. So this is due to Gerbert Dillon and Jeremy Taylor. This is the equivalence of universal. It's the universal monodromic version of Bezrukovnikov's equivalence relating to realizations of the affine Hecke category. So this is the universal monodromic affine Hecke category. So at that level, like this conjectural equivalence of 2 categories here should be read as some like lift of the Dillon-Taylor equivalence here. And so this is the reason why we like these sort of universal monodromic equivalences, is that they tend to be the ones that naturally kind of categorify. This statement here is supposed to like you're supposed to get statements like this from statements like this. Let me say that there's also a more naive categorification you could do to these 2 categories, where sort of instead of taking categorical trace, you can take a sort of naive trace, or the sort of what people call the vertical trace maybe, where you just sort of apply periodic, or you apply like Hochschild or periodic cyclic homology to everything in sight. And if you do that, then you recover some kind of, I'll say on this side, you can also recover, well, okay, maybe I don't want to go into this so much, but you can also recover a universal monodromic equivalence of the usual Hecke categories, and that was something done by Jeremy Taylor and Jens Eberhardt, where they constructed some sort of equivalence between B times B constructible sheaves on G and some kind of like the K0 of this thing here. And you can similarly do something similar over here, where you could study B constructible sheaves on X. So maybe I'll say this, also a conjecture, which is that B constructible sheaves on X should be equivalent to some decategorification of this by taking, HP, or by taking K0, if you like, which should give you some category of what I think Eberhardt calls them K-motivic sheaves. I'll just call them K sheaves. K sheaves on X check mod B check. So whatever this category is, it's something like the usual category of sheaves, except instead of computing equivariant cohomology, they compute equivariant K theory. This should be acted on by the usual Hecke 1 category, the universal monodromic Hecke 1 category, which over here is B times B constructible sheaves on G, and over here is K sheaves on G check mod B check mod B check. And so this equivalence here, sorry, my microphone cord. This equivalence here is due to Jeremy Taylor building on some works by Jens Eberhardt, and Eberhard and Tev have a follow-up as well. So that's this equivalence of Hecke categories here. So you can
this equivalence
what?
related to Kazoo duality between the point?
Sorry, can you
How
you
is
say
this
that again?
equivalence related to the Kazoo duality between? How is this equivalence
so-
related to Kazoo
Yeah.
duality between sheaves on G mod B mod B and G?
Yeah, so this is the ungraded universal monodromic version of causal duality. So like part of the thing is that when the universal monodromic like equivalent, like how to say, if I erased I could erase the K here and just study usual sheaves on G check mod B check mod B check, and that would have the same effect as over here looking at B times B equivariant sheaves on G, which involves like actually trivializing the toric the torus monodromies here, those categories have some extra grading that you can use to define a causal duality. Here I've passed to this universal monodromic category, which means having to do this K-sheaf thing here, which already screws with my grading because now like the B check equivariant K theory of a point is only 2 periodic. But it still has the sort of same structure of, I mean, the way Taylor proves this equivalence is like he constructs the tilting object inside of here, which forms some kind of like additive subcategory that you can match up with the Bott-Samuelson objects inside of here, and you can relate both of them combinatorially to Zergel bimodules. And and those things are like the simple objects here and match up with the tilting objects here. So that's my potted explanation of how this relates to causal duality. And so part of this conjecture here is sort of laying out a program or something that like you might like to develop some kind of Zergel theory for spherical varieties. But if someone gives you a spherical variety, like you also have some conjectural now equivalence of categories here. And like we know that kind of the right kind of combinatorics algebra, whatever, to interpolate this between these two kinds of categories is called like Zergel bimodules. And so there should be some kind of like Zergel bimodule type thing for these. Another way to say that is that like both of these categories have like these monoidal categories have diagrammatics that you use to describe them. And that like there should also be diagrammatic presentations of these that make it clear how they're modules for that diagrammatically defined Zergel bimodule category. So yeah, I worry that this is getting a bit technical at this point, but this is just to say that like if you know that like you have two things that are dual to each other, then you can get an extremely rich set of conjectural relations between various categories associated to them, various invariants associated to them, and they recover, and those conjectures recover module categories for various flavors of Hecke category or Hecke 2 category or affine Hecke category. Okay, so let me state one theorem that I can state about this non-abelian case, and then maybe I'll go back and after that try and explain. I can end my talk by explaining a little bit about what perverse sheaves of categories are, unless anyone has other questions.
It's the idea that you will match up some collections of objects on both sides and then prove that do the same procedure to them to generate the categories.
You're asking how would I prove this conjecture here?
Yes.
Well, okay, the best proof would be to just prove this conjecture here, and then take the appropriate decategorifications. But let me say that, in a lot of cases, so I should say that, so let me name some names here. For the non-universal monodromic version of this equivalence, I wrote all this down so that I could make contact with some previous papers, so that if you actually look at B equivariant sheaves on X, and you don't look at K sheaves here, then this is essentially some conjecture that appears in this paper of Finkelberg, Ginsburg, and Trapkin, where they have some particular examples of X and X check that are maybe the most interesting examples. These ones coming from sort of representation theory. Well, I don't know, maybe everything comes from representation theory, but there are examples that look like, I don't know, n by n matrices or n by m matrices or whatever. And there's actually various conjectures in that paper. I mean, the first conjecture is like even one categorical level or two categorical levels lower than this. It's like that the number of B orbits here is equal to the number of B check orbits here. That there's a bijection between the components of the corresponding Lagrangians. And then once you know that bijection, then you can sort of you can up it to some equivalence of modules for a Hecke algebra, and then you can up it to equivalence of modules for a Hecke category. And yeah, at every step, I don't know, there's some more combinatorics involved, but you're sort of building on like that you have the same components of the Lagrangian here, and what do those components of the Lagrangian correspond to over here? And then once you know how to match those up, then hopefully maybe there's a version of like over here, what you did is like you found tilting objects and matched them up with simple objects here. So maybe you should try and like find some like tilting type object that you can associate to each component here and match it up to some like simple type object over here. Of course, if you try and do all this by hand, it's probably going to be hard to match this up with the actual actions of these monoidal categories. So you want to be doing whatever equivalence you're giving here, you want to do it in a way that's manifestly compatible with the equivalence you gave over here, which is why I'm suggesting you try and do some like tilting stuff, or try and write some diagrammatics that matches up with this. I don't know.
So would this work for the general conjecture?
Sorry?
Would this work for the general conjecture?
You mean up here?
Yes.
Yeah, ultimately, I mean, this is going to be, ultimately you're going to want, we do want diagrammatic description. I don't know if I mean, I don't know. Certainly like, you're going to want some diagrammatic descriptions of these two categories, maybe. Like in the sense that like you might, in order to prove these things, like trying to reduce them to a kind of combinatorics. And that's a very noble quest. And I should say that like the quest for diagrammatics of these two categories is actually diagrammatics of this two categories should really be like the diagrams should really be counting some holomorphic disks inside of like T star X. So it's actually like telling you something very concrete about geometry. So there's some work of Mina Aganagic and her collaborators. I don't remember all the names on the paper, but they, I think Vivek Shenda and Peng Zhao and okay, I don't remember everyone on the paper, but they have some paper where they compute some Fukaya categories of I think multiplicative Coulomb branches by a kind of like diagrammatics that matches up with matches up with the KLRW diagrammatics for like KLRW algebras. And so like so in other words, like diagrams that people have been drawing to describe like Hecke categories really are actually counting holomorphic disks in the Fukaya category. And so you can imagine trying to write a diagrammatics for this two category, and it really is like telling you something about this like Fuder two category, like holomorphic disks and these Fuder balls inside of a hyperkähler manifold. So that would be a fantastic thing to do. We have not done that yet. I don't know. Partially, I don't know. Three-dimensional diagrammatics is probably more difficult than two-dimensional diagrammatics, but also maybe more rewarding. Let me state one theorem that I can state about this. So that I know right now this might seem like I'm just kind of blathering on and like, how can we possibly, like prove any of these things when we don't know what they are? So theorem with myself and Justin Hilburn in progress is that we do know an equivalence of two categories of this form when G is SL2 acting on C2. So let G equal SL2 acting on C2 and G check equal PGL2 acting on PGL2 mod GM. Sorry, it's the cotangent bundles of these things. Okay, SL2 acting on the cotangent bundle of C2, PGL2 acting on the cotangent bundle of PGL2 mod GM. And in that case, then we can define perverse sheaves of categories, be constructible perverse sheaves of categories on C2. And we can prove that this is equivalent to incoherent sheaves of categories on PGL2 mod GM that are B-check equivariant. So we can actually define this equivalence of two categories. In fact, we can do this for, you can let G equal SLN acting on T star C to the N, and you can also write this down, only you have to do a sort of micro-local version on the right-hand side because you're no longer a cotangent bundle over here, but it's still something that we know how to do, which I think has to do with the fact that, oh yeah, this and moreover, by taking trace, we get a statement of the form that Iwahori constructible sheaves on the loop space of C2 are supposed to match up to incoherent sheaves on the loop space of PGL2 mod B-check mod GM. So like maybe the fact that we're able to do this, but not, but we don't know a general description of perverse Schober's, probably at least partially has to do with the fact that C2 is affine, which because, if we believe that like taking trace takes you from here to here, then, this loop space of C2, it makes a lot more sense when C2 is affine. And you might need to be very careful about things otherwise. But this is at least one case where we can sort of fully make sense of what this two category is and make sense of and prove that it's equivalent to this other two category. So again, this is some evidence that like I'm not just making a bunch of wild conjectures here. So if we end at 4, that leaves me with 5 minutes left. So maybe now I can tell you what a perverse sheaf of categories on A1 is. And that can be a good way to end the talk. So perverse sheaves of categories on A1, on C, say. So maybe actually, first of all, let me remind you what a perverse sheaf is. So a perverse sheaf on C with respect to that's constructible with respect to the C star stratification is given by the data of a pair of vector spaces called vanishing cycles and nearby cycles with canonical and variation maps between them. Let me just call these X and Y. And these X and Y satisfy the property that XY minus 1 and YX minus 1 are invertible. And maybe I'll just say that. Yeah, so 1 minus XY, 1 minus YX are invertible. I mean, you could also say that each one of these guys is equipped with some isomorphism, which you'll call T, and that these T phi and T psi, and that these 1 minus XY is equal to the relevant operator T. So the point is that they're invertible. So similarly, this notion of C star constructible perverse sheaves on C. So this notion of perverse Schober's first appears in work of Kapranov-Sheftman, although okay, they didn't define it as a two category, but the relevant objects were previously defined by Rina Ano and Ano Logvinenko under the name of spherical functors. And so what it is now I have a pair of categories, C phi, C psi. I have a pair of functors, F and G between them, which are an adjoint pair of functors. And what the adjunction gives me is the adjunction gives me a unit map from C phi to GF, and similarly a co-unit map from FG to the identity on C psi. And I can treat each of these things as a two-term complex of functors. So therefore, I can think of it as some other functor on C phi or C psi, and I can ask for these two-term complexes to be invertible. Or in other words, I can take the cone or cocone or fiber or cofiber of these things, and I can ask for them to be invertible. So this is like a pretty nice thing. I could give a whole talk just about this. Maybe I should have, just about the sort of like underlying category theory of this thing. And the point is that like really everything in this case reduces to like some combinatorics about understanding the two category of adjunctions, the free adjunction, and like what happens when you invert these objects, which are called the twists. So that's, I think, unfortunately, I'm out of time, so I'm not going to be able to say it. Let me just say that this is also known as this is also known as the category of spherical adjunctions. And I can tell you what perverse sheaves of categories are now on C to the N, stratified by the Borel subgroup of SLN acting on C to the N. And what it is it's going to be length n spherical complexes, or length n+1 spherical complexes. So this is going to be a chain of n categories with functors between them, such that each d is spherical and d squared is equal to 0. And so you can see that once again, the two category of perverse Schobers on C to the N with constructible with respect to the B stratification is like something you could really get your hands on. It's something that, you could imagine sort of presenting in a very combinatorial way. And in fact, you can relate it to some combinatorics of Iwahori equivariant sheaves on the loop space of C to the N. So it's about 4 o'clock now, so I'll end my talk there. Thanks for listening.